talking about... Okay, in class we were talking about orders of reactants. For example, if you look at this first rate equation that is written at the top of my paper, it's also at the top of your notes paper. This 0 right here is saying that A is 0 order, that reactant B is first order, and that reactant C is second order. We discussed in class how those orders can tell you things about the individual reactants, but we can also do something called order of reactions. See the difference between the word reactants and the word reactions? What we can do is take all three of those exponents, add them together, and see what they equal. In this case, they total 3. So the order of this reaction is considered third order. Now, knowing the order of the reaction can allow you to do some extra calculations. On your notes, you see that it talks about 0 order reactions, which are very uncommon. In 0 order reactions, the reactant concentration actually does not affect the rate at all. So there are reactions out there where the concentration of the reactant is unimportant. An example of that, it's not on your notes, but an example would be the decomposition of hydrogen peroxide. It decomposes at the same rate the entire time. Again, I told you the other day in class, we will learn why certain reactants don't contribute to rates a little later, pretty soon, but a little later. Now, if you do have a first order overall reaction, something like you might have a rate law of rate equals K times the concentration of A to the first, and that's it. There's no other reactant involved, just one reactant with a first order on it. Then we can use a special equation, which is this one here, to calculate the amount of time it takes to get to a certain concentration. So say you started at 1 molar and you wanted to know how long it was going to take to get to a half molar. And this equation will allow you to do that. So anytime you're doing a problem that involves time, then we're talking about these equations that we'll learn in this lesson today. Specifically, first order reactions have to use this equation in front of you. So if you read the example problem, it says a certain first order reaction. Notice they haven't even told you what the reaction was, but the fact that they've told you it's first order means we don't even need to know the balanced equation. I don't even need the whole rate law. All I needed to know was that it was first order. By knowing that it was first order, I know that I'm going to use that equation that we had just pointed out above. Now let's go ahead, before we get into this problem, and go through what each one of these variables are. They should be pretty familiar to you. These two ln's are functions in your calculator. So if you look on your calculator, you'll see your natural log button. Square bracket A is your concentration of your A, but this one right here with the little I in it means the initial concentration of A. And then the one with the little T on it means your final concentration. So if, like my example before, I said if you started with 1 molar, that would go here, and you were trying to find 0.5 molar, that would go there. K is your rate constant, just like your rate constant from your rate law. It's the exact same K value. And then T is going to be your time. Now, time does not have to be in any unit specifically, except that it has to match whatever time is in the rate constant unit. So please keep that in mind while you're working. So if we go back to the problem, it says a certain first order reaction has a rate constant of 4.5 times 10 to the negative third, S minus 1. Let's make sure everybody knows what S minus 1 means. S minus 1 is the same thing as saying 1 over S. So the unit on this rate constant is 1 over S. So time needs to be in seconds, since the time in the rate constant unit is in seconds. And they want to know how much of a 0.05 molar sample will have reacted after 75 seconds. So right here, this is your initial concentration. This will be your time. And that should be everything we need to be able to plug in and solve this problem. So we're going to take the ln of our initial concentration, which we just said was 0.050, minus the ln of our concentration at our time. Now that is what we are trying to find. So we're going to leave that as our variable. And then it'll be equal to K, which is 4.5 times 10 to the negative third, times our time, which was 75 seconds. Again, I needed to verify that the seconds here match the time part of that unit. And it did. If it doesn't, you just need to convert it so that it does, in fact, match. So now we just need to do some math. If you plug in your calculator, ln of 0.05, you're going to get negative 2.9957 minus, we're going to leave this part alone because that is our variable, and then 4.5 times 10 to the negative third times 75 is 0.3375. I'm going to add over the 2.9957, so on this side I'm going to be left with negative of ln AT. And on the other side, we're going to have 3.3332. Now, to get rid of an ln, you can't have a negative on it. So we're first going to have to multiply both sides by -1 to get ln to be positive, which is going to make this side negative 3.3332. And then to get rid of an ln, it's quite simple on your calculator. You're going to hit the second button and then hit the ln button. When you do that, you're going to get the inverse of the natural log, which should be a little e. So both sides are going to be raised to this e. It's going to cancel the ln out on that side. So in your calculator, you should be putting second ln and then negative 3.3332. When you do that, you end up with a concentration of 0.036 molar. Now the problem with this answer is it's not actually done. This right here is the concentration at 75 seconds. That's what that value means. But the problem said how much of the sample will have reacted. That's how much is left, not how much reacted. So we have to do one more little math step. Our initial concentration was 0.050. If we subtract what's left, we're going to find our final concentration, which comes out to be 0.014 molar. And that would be your answer of what was reacted. If they had simply asked what was left at 75 seconds, this would have been your answer. But because it said how much will have reacted, we needed to know the difference between those two. Now, second order reaction is very similar. You can see on your paper two versions of rate laws that would both be considered second order overall. This one only has one reactant and its exponent is a 2, so that's an overall order of 2. This one has a 1 and a 1, and if we add that together, we get 2. This type, we won't be doing these time calculations for. The equation is much more advanced than the one we're going to be using it for. We're only going to work with second order reactions in which there's only one reactant contributing both order. So if you look, this is the equation that we're going to be using. It looks very similar to the first order one with some important notable changes. Same variables, we're just not using ln anymore, and the T concentration, the one at the time, is listed first this time. Again, the problem doesn't even tell you the rate law. It just says it's a second order reaction. That gives you permission to use the equation above. So we will be using 1 over AT minus 1 over AI equals KT. So plugging in what we know, we don't know the concentration at AT. We do know the concentration originally. It's given in the problem here. We know our K value is 3.6 times 10 to the negative second, and that is in, what do we have here? Yeah, that is in 1 over molarity times seconds. And then the time that is involved is 135 seconds. So I will be multiplying by 135. Double check that seconds part. See, seconds and seconds. So we're good. If it's not, again, it's just a simple conversion, but you just make sure you check. So now to do the math, I'm going to have 1 over AT minus, if I do 1 divided by 0.05, I get 20. And then on the other side of the equation, 3.6 times 10 to the negative second times 135 is 4.86. Now if I add over the 20 so that I can get 1 over AT by itself, I'm going to have 24.86. And then I can take the inverse of both sides. It's usually the easiest way to do this type of problem, or just cross multiply and solve for AT. we end up with a value of 0.04022 molar. But again, this is what is left at 135 seconds. The problem didn't ask me that. It said how much will have reacted. So I need to take the initial concentration, which was 0.050, and I need to subtract what was left to find out that this is how much was actually reacted.